This is the Spring 2024 Organic Chemistry 2 Exam 1 review. Question 1 states, what is the name of the molecule shown? So again, the first rule of naming is finding the longest carbon chain, which I'll highlight here in green. So once we do that, we can see that there are 5 carbon atoms. So 5 is going to be a pentane derivative. And we can see that it's a conjugated diene. So we're going to change the ane to a diene ending. And we can see that if we start numbering 1, 2, 3, 4, 5, the double bonds start at 1 and 3. So we're going to call this a 1, 3 pentadiene. We can see at the 3 position there's a methyl group. So we're slowly building up this name. So 3 methyl, 1, 3 pentadiene. And then lastly, what we have to consider is the double bond between carbons 3 and 4 is tri-substituted. So it could possibly have EZ or cis-trans geometry, so we need to figure that out. So you look at the sp2 hybridized carbons, you assign priority, again, using the atomic number. So we can see that on the carbon 3, priority is going to go towards the 2 carbon rather than the substituent. So we'll call that 1. And then on carbon 4, the priority is going to go towards carbon 5, so we'll call that 1. And again, we're comparing to these other substituents. So because they're on the same side, they would be cis or Z, and so you would append that in front, Z 3-methyl 1,3 pentadiene. Question 2 asks how many unique hydrogen sets are there in the molecule shown. And so just go ahead and draw in your hydrogens. And so the thing you have to consider here is that the hydrogens on carbon 1 are both different because they have different relationships to the hydrogen on carbon 2. So this is going to be 1, 2, 3, 4, 5, and 6. So 6 unique sets. And again, the difference is these here are cis, and then these here are trans. So those hydrogens on carbon 1 are different, so they're counted as a unique set. Question 3 asks, using the Woodward-Fieser rules, calculate lambda max for the molecule shown. So the base value we said was 217 nanometers. And so we see that for the 1,3-butadiene, we have 2 oxychromes. So those were worth 5 nanometers a piece. That's 10 nanometers. And so total we get 227 nanometers for the lambda max. Question 4 here, based on your prior calculation of lambda max, would the molecule shown have a color in the visible region of the electromagnetic spectrum? The answer is no. Again, you have to be between 4 and 800 nanometers, and so we're only at 227 when we calculated using the Woodward-Fieser rules. Question 5, given the Diels-Alder adduct shown, what diene was used in its preparation? So again, a Diels-Alder gives a cyclohexenone, or cyclohexene, excuse me. And so, again, that's a cyclohexene. And when you're thinking in the retrosynthetic sense backwards, the bonds are going to move like that. So you can get your diene and then your dienophile. And so that's your 4 plus 2. So in the molecule, you can identify there's the alkene of the cyclohexene. And so when you do the retrosynthesis of this, you're basically going backwards, and I'll try to keep the drawing in the same orientation. So there's your diene, you have your bridgehead oxygen, and then you have your dienophile. And so if you unravel that and draw it sort of flat, this ends up being furan. And this ends up being acrylonitrile. So the answer to 5 is furan. Question 6 is asking if the starting diene, if this is aromatic, and the answer is true. So furan is an aromatic compound, so it obeys the Huckel's rule. You can make a frost circle with it and obey all of the rules. Again, it has the 4n plus 2 pi electrons. It's flat. All atoms are sp2 hybridized. So when you're looking at the lone pairs, oxygen's lone pair, you have, again, a lone pair in an sp2 orbital, and then a lone pair in a p orbital. And we had discussed that in class in relation to parole, which is another aromatic heterocycle. Question 7, what dienophile was used? Again, that's going to be this part of the molecule here. So that ends up being this alkene bearing a cyano group. And that's called acrylonitrile. What is the molecular formula of this molecule? So you're starting from again furan, and these are combining. You're not losing any atoms. So you have C4H4O plus C3H3N. So if you add those together, you get C7H7NO. And so again, the elements after the carbon and hydrogen must be in alphabetical order. What is the molecular weight of this molecule? So you have C7H7NO. So you have 12 times 7. That gets you 84. 1 times 7 gets you 7. 1 times 14 times 1. And then 16 times 1 is 16. So how do we want to do this? 84 plus 16, that gets you 90, that gets you 100, plus 14, that gets you 114, plus 7, that gets you 121. So that's the molecular weight. Identify the carbon atom that would be involved in a sharp, very intense signal in the IR spectrum around 2200. Again, that's the nitrile group. So you should have targeted the carbon right here. And again, the reason for that is you have to understand that when you expand out the nitrile into the Lewis dot, it's a carbon-nitrogen triple bond, and that's the region in the IR that you would see that. Given the deals all their adducts shown, how many unique carbon atoms does it have? So we found before that there's 7 carbon atoms. They're all unique because there is no symmetry to this molecule. So the answer is 7. How many hydrogen neighbors does HA have? And again, so this is the carbon-bearing HA. So you have to look at its carbon neighbors, of which there are 3. So this carbon has 0, this carbon has 2, and that carbon has 1. So you have 3 total neighbors of HA. What is the dihedral angle between HA, CC, HB? So remember that a dihedral angle is the intersection of 2 planes or 2 bond angles. So here's HA to C, C to C, C to HB. And you can kind of tell the way it's drawn, or if you make a model, the dihedral angle is 0. So those are eclipsing hydrogens. And what is the coupling constant between HA and HB? So this is from the Karplus equation. And when you go on the Karplus curve, at 0 of a dihedral angle, it's approximately 13 hertz. So I accepted 11, 12, 13, and 14. Or no, excuse me, just 12, 13, and 14 hertz. So 13 plus or minus 1 was accepted as a response for this. So what multiplicity would you expect to see for HA? So there's 3 neighbors. So 3 if you're using the n plus 1 rule. So 3 plus 1 is 4. That would be a quartet. To a first approximation, however, a better response for that is instead of a quartet, a doublet of doublets. And the way that arises is the dihedral angles of HA to all of the neighbors are all different. And because those angles are different, the couplings are different. And then you consider each separate. So basically you'd have a doublet between A and B, a doublet between A and C, and then a doublet between A and we'll call it D down here. So that's a certain angle, 0. HA to HC is another angle, so that's a certain coupling, and then HA to HD. So those 3 angles are different. Therefore, you're going to have 3 different couplings. So it would be a doublet of doublets. What reaction type of electrophilic aromatic substitution has benzene undergone? So it's telling you that benzene has reacted with some electrophile to form a monosubstituted benzene. And so a monosubstituted benzene, if you look at the aromatic region, you have three unique signals, and that's what you see. So the ortho hydrogens, those are going to occur as the doublet. The metahydrogens, the larger triplet because there's two of them, and then the parahydrogen, the smaller triplet because there's one. And so you see that. So you're assuming this is two hydrogens, one. That gets you your total of 5 aromatic. And then you're looking at the other signals here. There's two of them. There's a septet and a doublet. And so we'll figure out what that is a little bit later. But the key to answering this question really lies in scanning the carbon NMR, where you see this signal down here at 200. That signal is telling you that is a carbon of a carbonyl. And how do you get a carbonyl? Through Friedel-Crafts acylation. So what electrophile was benzene reacted with to give the proton and carbon NMR? So if it's an acylation, it has to be an acid chloride or an anhydride. So you have the carbonyl carbon, and then basically what you're figuring out is the other stuff attached to it, and that you get that from this data here in the proton NMR, so the septet in the doublet. So if a signal occurs as a septet, that means it has 6 neighbors. So if a signal occurs as a doublet, that means it has 1 neighbor. And so the only thing that you can draw that will give that signature is an isopropyl group. So you have these two methyl groups that integrate to 6. So 6 plus 1 gives you your 7. That's how you end up with the septet. Then you have your doublet. So the integration of this would be an integration of 1 for the septet, and then 6 for the doublet. So that gets you your 2 unique aliphatic sets in a ratio of 6 to 1. So you plug those 2 fragments together, the acid chloride part, the isopropyl part, and so the IUPAC name of this would be 2-methyl propanoyl chloride. It's also called isobutyryl chloride. That's fine as well. So the IUPAC or common name was accepted as the right answer. What is the molecular weight of the product that gives these NMR spectra? So what you end up with is this ketone. So you have 6 carbons for the aromatic ring, 7, 8, 9, 10, including the ketone side chain. Then the number of hydrogens, there's 5 on the ring, plus 1 for the methine, so that's 6, and then 6 for the methyls, so 12. And then oxygen, so you have 12, 16 times 10 times 12 times 1, that gets you 120. That gets you 12. that gets you 16. So we'll do 132 and then add 16 to that. So we get 8 for 148 is the molecular weight. How many degrees of unsaturation does the unknown compound have? So again, the aromatic ring is 4. So you're making that assumption just by looking at the presence of signals in that region of the NMR. And then in the carbon, as we said, the pCat 202 is a carbonyl. So that's a degree of unsaturation. And again, a monosubstituted benzene gives you 4 degrees of unsaturation. So the total is 5. But from our molecular formula, we had C10 H12O. We can also calculate it from that. So where N equals 10, we should have CnH2n plus 2. So 10, 22. So H22 minus H12 is H10. A degree of unsaturation is H2, so that gets you your 5. What is the name of the unknown substance? So the common name is isobutyrophenone. And the IUPAC name was 2-methyl-1-phenyl propane PAN-1-one. So again, with nomenclature, a number is separated by a hyphen. A letter is separated from a number by a hyphen. So see these letters L and P, they're separated by the hyphens. They got the number in the middle. And as we said in class, you can put the 1, the newer IUPAC rules, put the 1 before the main functional group at the suffix of the name. The older ones would put the 1 in front of the largest carbon chain count. If you added commas or spaces or extra things like that, you did not get full points for this. So this run of questions is asking you about a sequence of reactions to produce a compound from benzene. You're given some data and ultimately figure out what the structure is and how to name it. So benzene has undergone a sequence of reactions to produce a mass spectrum shown. What halogen atom does the molecular formula contain? So it says right there a halogen atom. So that's F, Cl, bromine, Br, or I. We learned that F and I are not really indicative in mass spec in the parent region, but chlorine and bromine are. Chlorine has a 3-to-1, bromine has a 1-to-1 ratio, and again, what you're looking at is the heights of these peaks. So that's clearly not 1-to-1, so it's 3-to-1, so the answer is chlorine. So you have a chlorine fragment, that's 35 atomic mass units. Let me specify that further for the 142 parent. And then for the 144 parent, that's M plus 2, that has the 37 Cl. Again, that's what the 3-to-1 ratio means. How many unique carbons does the unknown substance have? So this is just counting from this data. 1, 2, 3, 4, 5, 6, 7. So it's telling you benzene, There's 6 carbons there. In benzene, however, the uniqueness is 1, but we're reacting it with an electrophile. So now you have a monosubstituted benzene. Depending on what that electrophile is, you may have added a carbon or not. So now what you've done is increase the uniqueness of the monosubstituted ring. So now you're up to 3 unique carbons due to the symmetry. You have the ortho, the meta, the para. So I'm going to call this E1. Then you're going to do another series of reactions, but for now we're just going to say E2. And again, depending on what E2 is, or depending on what E1 is, it's going to direct ortho meta para. So you have ortho meta para. And then from that, the symmetry elements, as we talked about in class, are going to help you figure out what the substitution pattern is. So really, you can eliminate a para substitution at this point, because that's going to give you the lowest amount of unique carbons in the benzene region. You can see that in the aromatic region, there's 6 unique carbons. So that's going to leave you with ortho or meta substitution. If it was para, it would have to be 4. How many unique sets of hydrogen atoms? So there's a set 1, 2, 3, 4, 5. This answer was 5 unique sets. Now, one thing I want to point out, triplet, doublet, sort of looks like a triplet. We'll call it a singlet and a doublet. So you have 4 unique sets in the aromatic region. And even though we're jumping the gun a little bit, we said that E1 has to be either ortho to E2, E1, or meta to E2. And so now you can get an idea of really how the reaction occurred, because if you assign the multiplicities, this will be a doublet, a triplet, triplet, or doublet. And for the meta, this would be a singlet, or excuse me, singlet, doublet, triplet, doublet. So it's looking more like it's meta substituted at this point. So what substitution pattern does it have? And so we reviewed that in the prior slide here. Triplet, doublet, doublet, and then singlet. Even though there's some a little bit of shouldering on there, it looks more like a singlet than it does another triplet, which would be found in the ortho. So let's draw out so E1, E2, that's going to be a singlet. And so the reason it has that little extra bit is due to a very small coupling. So from this bond through to this bond through to that bond, you get this small shouldering that you see right there. That's called a W coupling. But again, visually, you know that this looks different than that, which has a normal triplet looking pattern. How many atomic mass units are remaining after the carbon and heteroatom are subtracted from the parent ion? So we said from the mass of the parent, the parent ion with 35 Cl was equal to an M to Z of 142. So 142 minus 35, again, that's the 35 chlorine contribution. 142 minus 35 gets you 107. We saw that there were 12 times 7, so that's 84 for the carbon. So we're going to subtract out the C12 contribution. So minus 84 is going to give you 23. And so as we'll see, we know it's an aromatic compound. That takes up 4 of the 5 unique 1H signals. So you're really not dealing with a whole lot of hydrogen atoms remaining. So there has to be some other heteroatom present. So we saw from the prior calculation, we have 23 mass units remaining after we subtracted out the Cl35 plus the 7 carbons. So let's do some thinking about this. We said there were 5 unique 1H sets. So 4 of those sets were unique in the aromatic region. And so what that's telling you is that ratio is 1 to 1 to 1 to 1. So there's 4 total there. So you can see you have one more unique H set, but that's not going to give you a whole lot of hydrogens for this. So that other set was approximately 3.8 ppm. We know that nitrogen is not present because the parent was not odd. So that really leaves us with oxygen. So if we do 16 for oxygen, 4 for aromatic H's, that's going to leave you with a mass contribution of 3. So that belongs to the last signal, 3.8 ppm. And so what is that? That's going to be OCH3. So again, the chemical shift of 3.8 indicates that those 3 hydrogens are bonded to a heteroatom because they're shifted further away from 0. So now you have these fragments that you've put together. A disubstituted benzene, a methoxy, and then a chloro. Based on all the prior questions, what functional group is present for the singlet? So as we described, so that's going to be OCH3. So 1, 1, 1, 1, 3. So you have total 7 hydrogen atoms. The chemical shift of 3.8 indicates O, and so OCH3. So if you put methoxy, I also gave credit for ether in this problem. What number carbon atoms, or what number carbon atom on the aromatic ring is bearing the hydrogen atom that gives rise to the triplet? So this triplet at 7.19. So at this point, we're working with the meta-substituted pattern as our claim. So we said singlet, doublet, triplet, doublet, and if you number 1, 2, 3, 4, 5, 6, the answer is going to be 5. That gets you your triplet. So what series of reactions using the reagent guide that was posted in Canvas will give you that. So because you have a meta-substituted pattern, the first thing you want to do is put on an electron withdrawing group onto the ring is E1. So benzene, we're going to do a nitration, so HNO3, H2SO4, and so that was A9. So NO2. Now we're primed to do a 1,3 electrophilic aromatic substitution. So we want to do chlorination with E6. Again, that's your Cl2 aluminum trichloride. So NO2, Cl, and then now you have the pattern. So what do you need to do is a series of steps that transform the nitro group. So you have to transform that into the oxygen. So once you get the phenol, then you're going to do an acid-base reaction to get the alkoxide, and then an SN2 reaction to install the methyl group. So we saw taking the nitro group down to the amino group is a reduction. So you could have used any of the reagents listed here. So R5, so R is the reducing agents, R5, R6, R8, R9. Now we need to form the diazonium, and so that's reagent O8, so Na, NO2, HCl, and so we're calling that an oxidation, so that's why it starts with the O. So that gets you the N plus Cl minus Cl, that's your diazonium. Then from there, we need to install the oxygen, and this is where many of the responses were incorrect. I think A1 was chosen by a lot of people. Again, you need a nucleophilic oxygen, so that's going to be N6 was your copper oxide. So again, that matters that you chose the right oxygen source there, so OH, Cl. And now we need to do treat with a base, so you could use B1 or B6. So you need a pretty strong base. Again, you want to form the alkoxide as the primary product. You don't want an equilibrium, so you get O minus Cl, and then you're installing 1 carbon with an electrophile, E17, that was the methyl iodide. So if you put that all together, the form it should be like is A9, E6, R5, O8, N6, B6, E17. And then finishing off the exam, what is the name of the unknown product? So from all the prior questions, accepted a couple different correct responses here. So the common name meta, chloroanisole, or 1-chloro 3-methoxy, no L, 3-methoxybenzene. So either of those would have been accepted as correct. I would say, again, with the new format of these exams, pay attention to the short answer responses. Make sure that you're exactly correct. The format of the rest of the 4 module exams will be the same with the iClicker, with short answer, numeric, multiple choice, and target. So, you can expect similar questions on those exams where you're given, these clues about the product, and then you're slowly building up a case to prove what the structure of the unknown product is. And so again, you're definitely encouraged to analyze the data, write out the clues that you see. What do you not see? For example, in mass spec, if you don't see the odd mass, it cannot have nitrogen. Pay attention to IR data. Pay attention to the chemical shifts in the carbon and the proton. What are those things telling you? What fragments do you see? Start playing around with connecting the fragments to make sure that all the data is consistent and it doesn't sort of disagree with another piece of data. So again, that was a review of exam 1 for the fall or the spring 2024 Organic Chemistry 2 cohort.